Okay, good afternoon, everyone. Welcome to the next session of the Special Functions and Number Theory seminar. Our next speaker is Dr. Fatma Cicek from Indian Institute of Technology, Gandhinagar, and she'll be talking on the logarithm of the Riemann Zeta-function near the non-trivial zeros. Over to you, Fatma.
Thank you, Atul, for the introduction and also for inviting me to speak. And thank you everyone for coming to my talk today. So yeah, the topic is from my PhD thesis, which I recently finished with my advisor, Steve Gonek at University of Rochester. And what I want to do is I want to begin with an introduction to the theory, which includes some basics of the zeta function and also Selberg's central limit theorem. So the zeta function is given by this well-known infinite series in the half plane when real part is bigger than 1. It also has this Euler product expression. So you can see that this holds in the same region by expanding this negative first power using the geometric series and using the fundamental term of arithmetic. So zeta also has an analytic continuation to the whole complex plane. This is also called a monomorphic continuation because it will have a simple pole at s equals 1. So an important property of the zeta function is its functional equation, which is given by this last equation on this page. And this relates the values at s to its values at 1 minus s. So from here, you can see, for example, that when s is 0 on the left side, you can see that the pole of the gamma function at s equals 0 will give us the pole of the zeta function at 1. And the other poles of the gamma function when s over 2 is a negative integer, then those will lead us to zeros of the zeta function when s is a negative even integer. So these will be called the trivial zeros. And another thing you can observe from here is that from the start, from the infinite series of the zeta function, we know that zeta is real valued when s is a positive integer. And from the functional equation, you can also see that s is actually real for any real s. So that will also give us a symmetry with respect to the real axis. So using these symmetries with respect to the real axis, you can see that from the functional equation, we will have a symmetry with respect to the critical line, which is when real part of s is 1 over 2. So these symmetries will simplify our discussion for the zeta function. So instead of focusing on the whole complex plane, we can just choose to focus on some parts of the complex plane. So let's consider the zeros on this picture. So these green marks, they are the trivial zeros. And zeta is known to have non-trivial zeros from the theory of complex analysis. So infinitely many zeros. And it is known that all these zeros, they lie within this so-called critical strip. So when real part of s is between 0 and 1. It is also further known that on the edges of this region, so when real part of s is 0, or when real part of s is 1, we don't have any zeros. So all these zeros, they lie inside the region. So these non-trivial zeros are predicted by Riemann to all lie on the critical line. So they all are expected to have real part 1 over 2. And so far, we don't know any zero that is off the critical line. Okay, so we know that there are infinitely many non-trivial zeros. So we want to sort of try quantifying the count of zeros. So we let NT denote the number of non-trivial zeros within this gray region here. So the zeros will have a height up to t. And we can just focus on the zeros that lie in the upper half plane, using the symmetries of the zeta function. So we have a formula for this NT function. So this is called the Riemann von Mangold formula. When you look at this, the main term is t over 2 pi log t, or something like that. And the other terms, they are of smaller order. Everything else is of smaller order than that. So asymptotically, n of t behaves like t over 2 pi log t. And I should here mention that this argument function is defined as an increment of any continuous branch here. So it will be defined in a special way. So at 2, you will just pick, say you pick the principal branch. So argument of zeta 2 is going to be 0. And then from 2 to 2 plus it, the branch will have some variation. And then from 2 plus it to 1 over 2 plus it, that will have another variation. And the total of these will give you the argument of zeta at the point 1 over 2 plus it. And if 1 over 2 plus it happens to be a 0 of the zeta function, then we will just define the argument at that 0, argument of zeta at that 0, to be the averages of the left and right limits. So that will just be a definition as a convention. Okay, so these are the things that we know about the zeros. And we also have some conjectures on those zeros. So the most famous one is probably Montgomery's pair correlation conjecture. So remember, n of t is like t over 2 pi log t. So the average spacing is between consecutive zeros is about 2 pi over log t. So when you look at the difference between zeros in that scale, you can look at that scale being between alpha and beta, and that will be given by the integral of this function 1 minus sine square over pi x to the 2. So this function is called the pair correlation function for the ordinates of the zeros. So this conjecture doesn't assume the Riemann hypothesis, by the way. And I should also say that this delta 0, this is a term for a possible correction that may be needed when if alpha is less than or equal to 0, then you will be counting when gamma is equal to gamma prime, and in that case you will be counting the same 0. So in that case, delta 0 is going to be defined as 1. But if alpha is strictly bigger than 0, then delta 0 is just going to be set to be 0. Okay, so a consequence of pair correlation conjecture is the following zero spacing hypothesis. So in all the applications, this is used in addition to the Riemann hypothesis, which I just shorten as RH. And this hypothesis depends on a parameter alpha. So what do you do is you look at 2 consecutive zeros. So gamma n plus 1 is the one that comes right after gamma n. And if gamma n and gamma n plus 1, they correspond to a repeated 0 at gamma n, then gamma n plus 1 is just gamma n. So remember, the average spacing between zeros is about 2 pi over log t. So we look at this gamma n plus 1 minus gamma n being less than c over log t, just for any constant c that is small. And then we count the number of zeros when the next 0 is really close to that 0 gamma n. And we don't expect to have a lot of such zeros that are really close to each other. This is given with this hypothesis. And we also have the simplicity conjecture. So you can see that the zero spacing hypothesis sort of has some information on possible repeating zeros, but a stronger version of that will be when all the zeros are simple. We don't know any zeros that have multiplicity bigger than 1 so far. And in fact, even when you combine pair correlation conjecture with RH, we get that that 100% of the zeros are simple. So it is still possible that there will be a few, zeros that are not simple, but we just don't expect to have any that are not simple. Okay. So pair correlation conjecture is very well supported by numerical data, by the way. Okay, so the main topic of this talk is given by this Selberg's central limit theorem. So it is called central limit theorem because this main term on the right side in both of these statements, that is the distribution function of a standard Gaussian normal variable. So when the mean is 0 and the variance is 1. And when we start from the left side of this statement, this mu is the Lebesgue measure. So you look at the normalized measure of this set. So when real part of the logarithm of zeta lies in this interval. And A and B are just fixed real numbers. And we have an explicit error term for the rate of convergence, for how fast the distribution function of the real part of the logarithm of zeta converges to the distribution function of a standard Gaussian normal variable. And we have a similar statement for the imaginary part of the logarithm. And in that case, we have a better error term. So the difference between the error terms that is connected to the zeros of the zeta function on the critical line. So in the first statement, when 1/2 plus IT is just a zero of the zeta function, there isn't anything to say because that's just a discrete amount of points and that doesn't affect this continuous distribution. However, when 1/2 plus IT is still close to a zero, that will make the real part of logarithm really small. So that makes things really non-trivial, and that's the reason for the large error term here. So for the argument, you don't really have that type of problem, and the error term is slightly better. Okay, so this is stated for the critical line. But in fact, if you consider another vertical line, when the sigma, the real part, still depends on t in this way, so it is close to 1/2 by a constant over log t, then over that vertical line, we still have a central limit theorem that looks exactly like this. Okay, so how do we think about a theorem like that? So let's consider just the values of the real part of logarithm. So this slide, the graphic is on the slide is not mine, first of all. So this was a graph of Jeffrey Stoppel that I found online. So you can see that these are sort of really extremely low points. So these, they correspond to the zeros of the zeta function. So they just don't show up very clearly here, of course. And you just see some set of values of the function, and you don't see anything like the Gaussian bell curve here, of course. When you see the Gaussian bell curve is the following case. So this is another computation done by Stoppel. So the way you see the bell curve is the following. You pick some values of t that are equally spaced, and then you just plug them into your function, and then you draw a histogram for the values of your function. And when you do that, you see that there is a concentration of the values around 0. It still doesn't show up very well here, but you can see the shape of the bell curve showing up here. So this is a way of thinking about or interpreting this term. So now let's come to the title of this talk. So during the talk, I will assume the Riemann hypothesis from now on. And what I want to work with is these sequences. So I will look at the real part and the imaginary part separately. In fact, most of the time I will focus on the real part of the logarithm. And here rho just denotes an arbitrary 0 of the zeta function. Since we assume the Riemann hypothesis, we will write it as 1 over 2 plus I gamma. So gamma is the ordinate, and it is up to size t. And z is just a complex number that has a positive real part. So when you consider rho plus z, the real part will be 1 over 2 plus u, and that will lie to the left of the critical line. And the imaginary part of z, that can be positive or negative, but both of them, they have to have a size that is, you know, roughly the size of the average spacing between zeros. Okay. So in a picture, when you consider a picture, you can think of this one. So this green sequence is what we are looking at. We are looking at the real part of the logarithm of zeta, the values of that at this sequence. So when you remember Selberg's central limit theorem, it told us that the distribution, the continuous distribution on these vertical lines, for example, at sigma equals 1 over 2, or when sigma was between 1 over 2 and 1 over 2 plus c over log t, over these vertical lines, we had a central limit theorem for the distribution. So now what we are looking at is a discrete set of points that is given by rho plus z. So in a way, you can still expect to have some form of central limit theorem. The reason for that is that rho is something like 1 over 2 plus I gamma, and the ordinates gamma, we usually expect them to be some random looking numbers. They are random, but of course, they still depend on the zeta function, our function. So of course, it's not trivial to say that there is a central limit theorem in this case. Okay, so that's just some intuition. And the sort of similarity is that in a continuous case, of course, we just use the Lebesgue measure, and now we will use the discrete measure. And the set, the whole set has measure t, and now the whole set will have measure n of t, so the number of zeros with height up to t. Okay, so this is the first theorem that we have. So we need to assume Montgomery's conjecture in addition to the RH, and this is the case for the real part of logarithm. And what you see here is just basically some discrete version of Selberg's central limit theorem. Of course, there is a difference, and the difference is this m rho z, which is given by this equation here. So here, m of rho plus iv is the multiplicity of a possible zero at rho plus iv. So we don't really know if rho plus iv is another zero, but if it is a zero, then that will be the multiplicity here. If it is not a zero, then we will just have 0. M rho z will just be 0. And times, we just have m rho plus iv times this term here. So in sort of a discrete way, when rho plus iv is another zero of the zeta function, there will be a mean of the distribution, a non-zero mean of the distribution. The variance will still be 1 over 2 log t. And the error term is the same as we had in Selberg's central limit theorem. So we also have an imaginary part of logarithm result. So in this case, we only need to assume the Riemann hypothesis. And there isn't much difference in between this and Selberg's central limit theorem. The error term is still the same. Okay. So now for the rest of the talk, since I stated the theorems already, what I want to do is I want to speak of some ideas that goes into the proof of those results. What I want to do is I want to focus on the real part of the logarithm, just because it's actually sort of the harder one, and the imaginary part has a similar proof. And the proof will have these steps. So what polynomial approximation of the real part of logarithm, and then we will compute or we will say how to compute discrete moments of those polynomials, and then I will speak about how to find distribution function of real part of logarithm or real part of a Dirichlet polynomial. And finally, I'll just make some concluding remarks, which include a corollary on the logarithm of the derivative of the zeta function. Okay.
Fatma, I had a question before you proceed.
Yeah.
So you have taken z to be strictly bigger than 0, I mean the real part, I think. So
right.
Does Selberg already cover the case where z is 0, or what do you feel about that case?
I'm not sure if I heard it clearly, but Selberg's central limit theorem was also true for vertical lines here in between these two lines. So if you have if you had a vertical line over these green points.
Okay.
So Selberg's central limit theorem has a version, and that's like a generalized version that holds over vertical lines. That's not just a critical line, but lines of the form 1/2 plus u when u is less than c over log t, but u is positive.
Okay, no, what I meant was, does the Selberg theorem also cover the discrete measure when z is 0?
When z is 0, but oh, okay, I see. So when z is 0, though, you would have the real part of logarithm, and you would have to look at it at rho. So that doesn't really make sense.
I see. Okay.
Yeah.
Doesn't make sense.
In this case, yeah, it does. You need to make sure that z is not 0.
I see.
And what we do that, the way we do that is that the real part of z is positive, so z won't be 0 anyways.
Okay. Okay. Thanks. That answered my question.
Sure. Okay. So yeah, this was the plan for the rest of the talk. And now I want to go back to the proof of our terms here. So the idea is the following. So what we do is we take our function and then we approximate it by a polynomial. In our cases, since it's the real part of the function, we look at the real part of a polynomial. And the polynomial has to be short enough so that we are able to compute some moments. So let me speak about what that means. When I say moment, I mean the average of some power of your function. In our case, we will only look at average of an integral power of the function. So k here is an integer, is a positive integer. And when you look at moments of something like a real part of the polynomial, you will encounter terms that look like mixed moments. So you have jth power of your polynomial, and then you have the k minus j power of the conjugate of your polynomial. So we will need to compute moments like this. And in the end, when you compute moments, you will see that they match the moments of a Gaussian random variable with appropriate, mean and the variance. And a property of the Gaussian distribution is that it is characterized by its moments. So if you have the same moments, then that means that you also have your function also has a Gaussian distribution itself. So that will sort of give us the distribution. And the first step is the polynomial approximation. So we want to obtain a polynomial approximation to the real part of the logarithm of zeta. So what do we do is that we do that for the logarithmic derivative first, because the logarithmic derivative has a more mild behavior and it's easier to deal with. So remember the Euler product of the zeta function, but this is true in half plane when sigma or the real part of s is bigger than 1. And when you consider the, when you take the logarithm of this, of course, you will encounter a sum. And then when you take derivative of that sum, you will find a Dirichlet series that looks like this. So this coefficient lambda n is the von Mangold function. So that function will give you 0 when n is not the power of a prime. Usually what matters is that is for us is that not the higher prime powers, but just the primes. So in our case, instead of lambda n, it will be useful when we, okay, so first, wait, I need to mention the truncation of the Dirichlet series, sorry. So what do we want to do is we want to approximate our function by truncation of a Dirichlet series. So that will be called a Dirichlet polynomial. So we want to cut this series at x to the 2, okay? And when we do that, it will be useful if the coefficient lambda n also depends on x. So we define a weight function wxn, and the weight function will be weighted heavily on small primes or small prime powers. If you think of a Dirichlet polynomial that looks like, log p over p to the s, so when n is a prime, you can see that it will be, when s is 1 over 2 or close to 1 over 2, the small prime powers will be more effective for the distribution. So we have more weight on small prime powers. So our weight function will be separated from 2 to x, and then another weight from x to x to the 2. This is just a technical detail. Okay, so Selberg had a result in this case. I think, in fact, a version of this was proven by Landau earlier. So Selberg introduced a weight function. That's the difference that he had. He was able to approximate the logarithmic derivative by this Dirichlet polynomial. So this lambda xn, you can just think of it as something like log p over p to the s. And this is true for any s that is not problematic for the zeta function. So when s is not a pole, or when s is not a 0. And the important thing in this expression is this blue term that I have here. So this is a sum over non-trivial zeros. And the other terms, they are just terms that depend on trivial zeros or the pole of the function at s equals 1. So they are easier to deal with. So since we want to have Dirichlet approximation for the logarithmic derivative, we want to see what we can do for this blue term. In fact, when sigma is really close to 1 over 2, so it's close by a 4 over log x, it turns out that this blue term can be approximated in terms of primes. So this is a sum over the non-trivial zeros, but it turns out that it can be approximated in terms of a prime sum. This was a big step that Selberg was able to take in this direction. And the rest of the other terms, they're just rather small. So this is like a threshold for us, this red sigma value. So when sigma is big enough, we have a nice polynomial approximation, and the sigma is really close to 1 over 2. But we want to be able to even get closer than just 4 over log x. We want to get smaller than some constant over log t. So how do we do that is that when sigma is between 1 over 2 and sigma 1, we use a rather more general expression. This is given by Hadamard factorization of an entire version of the zeta function. This can be easily checked to be true. So when sigma is between 1 over 2 and sigma 1, in between those, we will use this expression. And now we are ready to integrate the logarithmic derivative and obtain an approximation for the real part of the logarithm at rho plus z. So the first step is this. So you can integrate from 1 over 2 plus u to infinity. The reason for that is zeta at infinity approaches to 1. And in the second step, we separate the integral from sigma 1 to infinity and then to 1 over 2 plus u to sigma 1. Observe that 1 over 2 plus u is the real part of rho plus z. And then when we separate that, it turns out that it will be useful if we add real part of zeta prime over zeta at sigma 1 plus it. And then since we added that, we will also need to subtract the same term. This is what we do in the middle term here. Okay, so we have three terms to deal with here. So the first one is from sigma 1 to infinity. And for the logarithmic derivative, we had a nice expression there. So we just integrate that, and then we find the the purported Dirichlet polynomial, a real part of Dirichlet polynomial from that integral. The second term is easy to compute because zeta prime over zeta at sigma 1 plus it is known. It has a known approximation, so we can approximate this easily as well. The hardest one is when we deal with the integral from 1 over 2 plus u to sigma 1, because 1 over 2 plus u can be really close to 1 over 2. So there we use this sum over non-trivial zeros. And it turns out that what we need to do is that if rho plus iv is a 0, then we would need to separate that 0 from the sum over rows for the sake of our approximation. So we do that. So that term will come with the multiplicity of the 0 at rho plus iv, and it will come with some factor. And once we do that, we will also have a term that will depend on the distance between an ordinate of a 0 and gamma plus v. So if this minimum here is too small, then this other term is going to be really large. So of course, in our approximation, we believe that that won't happen very often. And this is the step where we need to assume some hypothesis on the distance between these ordinates, gamma and gamma prime, so that we won't have too many pairs that are close to each other. And this is where the Montgomery's pair correlation conjecture will come in related computations. Okay, so this is all I want to say about the polynomial approximation. Now I want to speak about discrete moment computations. So as I said, we are interested in a short Dirichlet polynomial. So this length of the polynomial shouldn't be too large in relation to t. And we just use a basic identity to compute the real part, to compute moments of the real part of the polynomial. This is just the real part of z is the average of z and z bar. And once you write that down and take the k power, you see that you will have some combinatorial coefficients. And then you will have this blue term here. So for each j, if you compute this blue term, then you will be done. Okay, so let's look at that term for each j. Once you expand these j power and the k minus j power, you will have some primes pi and qj. They don't have to be distinct. They're just a bunch of primes up to x to the 2. And the sum over gamma, when you collect the gamma terms, you will have the I to the I gamma of this ratio here. So how do we compute the sum over gamma that looks like this? That's by the so-called Landau-Glonek formula. So this is the form of Landau-Glonek formula under Riemann hypothesis. There is also a form of this that holds unconditionally. So here you assume that x is a real number that's bigger than 1, and x to the I gamma, the sum of x to the I gamma is given by this term. So this is a nice formula that actually tells you how the zeros of the zeta function, non-trivial zeros, that are related to primes in another way. Is the lambda x, this is when x is a prime power, this won't be 0, and this will just give you the logarithm of the prime. But when x is not a prime power, lambda x is going to vanish again. So this is for x bigger than 1, and you have a nice error term that depends on x and t as well. And when x is 1, of course, you're just summing 1, so the sum is going to be n of t. When x is less than 1, that time you just take conjugates of the x to the I gamma, and then what you're doing is you're just replacing x with 1 over x to find the value of the sum for that x. Okay, so for any x, you have an expression. You have an expression for the sum of x to the I gamma. So now we want to apply this to our sum that we see here, and let's do that. So what we want is that this thing in the parentheses that has to be a nice number for us. So it can be 1, in which case we'll just get n of t. So this is what we call a diagonal term. And since you have a number of primes in this case, k minus j has to be the same as j, because these numbers are the same. So that will force us to have even k. And again, by Landau-Gonec formula, you can also have this ratio in the parentheses to be the prime p. And in that case, Landau-Gonec formula will give you minus t over 2 pi log p over square p. And you will also have, just by comparing the number of primes, you will have that k has to be odd. So we have these expressions for different values of k that we need to consider separately. And once you have a higher prime power, so when the power of the prime is bigger than 2, then you'll have a term like this, minus t over 2 pi log p over square root p to the a. And this will be multiplied with this factor, which will lead to a smaller looking term, because a is bigger than 2 here. So when the prime power is larger than 2, we expect to have smaller order terms. So suppose that we handle all these computations, and maybe in a few imaginary slides, suppose that we have written everything down, and you will get that when k is even, you will have an expression that looks like this. So let me explain these coefficients, beta k. So the beta k is the kth moment of the Gaussian distribution with mean 0 and variance 1. So it's actually just all the odd numbers that are less than k multiplied together. And this c is just the sum of 1 over p. So this 1 over p will come from the diagonal terms that we had, 1 over p to the 1 over 2 times 1 over p to the 1 over 2 when they are combined together. And by Martin's theorem, this is of the size log x, which is really close to log t if you choose x to be close to t. Okay. So what we have here is that these moments match the moments of a Gaussian distribution. And then we just have this k over 2 power of 1 over 2 c. And then, of course, we have the normalizing factor n of t. Okay. So when k is odd, then we again combine everything. And we have now some interesting looking coefficients. We have different looking coefficients. So for all k, we can compute odd moments of this Dirichlet polynomial. In the continuous case, this was not done by Selberg. The thing that allows us to compute odd moments of the Dirichlet polynomial is the Landau-Gonec formula, which gives something different for a discrete case. So once you look at this formula, when you divide this with the variance with the standard deviation, actually square root of c over 2, you see that the kth moment in that case, the normalized kth moment will approach to 0, because here you have c to the k minus 1 over 2 instead of c to the k over 2. And this actually is consistent with the odd moment of a Gaussian distribution. So asymptotically, when t tends to infinity, the moments match the moments of a Gaussian distribution, the integral moments. Okay, so these were all for the moments of the real part of the Dirichlet polynomial. Now I want to speak about how to say something on the distribution function. Okay, so since we computed the moments of the Dirichlet polynomial or the real part of the Dirichlet polynomial, we can also compute moments of our function. This is because we had an approximation for our function in terms of the real part of the polynomial. So we can compute moments of the function as well. It's just that the error terms will reverse in that case. And then since the moments match, the main terms will match the moments of a standard Gaussian distribution, we will have a central limit theorem that looks like this. So this is a weaker statement than I had in the beginning of my talk, because the error term is not as precise. So from the moment calculations, you just get that the error term just goes to 0 as t tends to infinity. So how do we make the error term precise? So that's the question that I want to speak about in this section of the talk. And before doing that, since this question is related to the following question, let me ask the following question. So where does this almost randomness come from? So zeta is just a deterministic function. So how do we get a central limit theorem for the zeta function, right? So this is a central limit theorem from probability theory. So you have a sequence of bounded random variables, but the important assumption is that the sum of the variances up to, say, n here, when n tends to infinity, that sum of variances has to diverge to infinity. If you have that, then the following distribution function that you see here, so you subtract the expected value from each random variable, and then you divide with the square root of the sum of the variances, then the distribution function of this random variable now that converges to the distribution function of a standard Gaussian that looks like this. Okay, so this is the usual central limit theorem. So how do we have a central limit theorem for the zeta function again? Okay, so this is the underlying idea. So in the polynomial that we had, so remember we were looking at the real part of this. So here, this p to the minus I gamma. These are the parts that sort of have a hidden randomness in them, almost randomness. So p to the minus I gamma, we can think of it as an exponential term like this. So here, this log p, the power, this forms a linearly independent set just from the unique factorization of natural numbers. So this set will be linearly independent over rationals. So what do we do is that since logarithm p is linearly independent, we try to approximate p to the minus I gamma by a random variable that looks like e to the 2 pi I theta p. So this e to the 2 pi I theta p, it will be uniformly distributed on the unit circle. But what do we do is we write it in this way, where theta p is uniformly distributed over the interval 0, 1. Okay? And for different p, different primes, the theta p's are independent random variables. Okay, so what do we do now is, instead of considering this Dirichlet polynomial, we look at this random polynomial that we see here. Okay, so what about this random polynomial? So this is our assumption on theta p. A nice property of these uniform distribution from this uniform distribution is that now when you integrate over 0, 1, you will see that when x is non-zero, this will be 0. But for x equals 0, this will just give you 1 over p to the 1 over 2 plus iv, or whatever you have. So using this, you can see that when you integrate your random polynomial to find the mean, so the average of the first power, that will give you 0. And since the mean is 0, the average of the second power now will give you the variance, and you will find that the variance will be C over 2. So this is what we had in Selberg's central limit theorem. This was the mean, and this was the variance. And when we compute moments again, we find that the moments match the moments of standard Gaussian with mean 0 and variance C over 2. So this is a perfect situation for us. These the behavior of these random variables. They describe the asymptotic behavior of the real part of the logarithm of zeta function. Okay, so this is a purported model for the behavior. So now this was the random, almost randomness part. So now back to our question. So we want to prove an explicit error term in this expression. So when you rewrite this in this way, this this sort of scripted one, this is the characteristic function of the interval a times square root 1 over 2 log t to v times square root 1 over 2 log t. So we want to estimate this sum in a precise way and hopefully obtain an error term. So I will just tell you how to precisely estimate this. So instead of focusing on our function, real part of logarithm with the minus m rho z term, since we have the polynomial approximation, we can just do that for the real part of the Dirichlet polynomial. We're allowed to do that using the polynomial approximation. So, excuse me. So here we had this characteristic function of an interval. Let me say that this a times the squared term is alpha, and this has to be b times the square root equals beta. So we are interested in finding smooth approximations to this characteristic function of the interval. And these smooth approximations, they will be obtained from the so-called Beurling-Selberg functions. So what the Beurling-Selberg functions do is that they allow you to use the Fourier transform, or in probability theory that will be called characteristic function. From that information, you can find something about the distribution function. Okay, so the Beurling-Selberg function is this f omega function that I have here. So it depends on a parameter omega, and it approximates the signum function, so that the signum function here gives you the sign of u. So when u is positive, for example, it will give you 1. And we have an explicit error term that is really good. When you look at this f omega, it's given by this sort of complicated looking integral, but the important part is having this sort of hidden u here, e to the 2 pi I u omega. So when you sum this over some u, you will have the Fourier transform appearing here. So the characteristic function, this is a nice exercise to see if you haven't seen something like this before. The characteristic function of an interval is given in terms of the signum functions and also the delta function, Dirac delta function. So when u is alpha, this will give you 1, but when u is not alpha, this will give you 0. So this is a general expression, and using this general expression, now you can approximate the characteristic function of an interval. So these are the Beurling-Selberg functions that we have, and the Dirac deltas, they also end up in these error terms. Okay. So now we wanted to estimate this sum of characteristic functions. So instead of the characteristic function now, I can just consider the sum of f of omegas, because f of omega approximates the characteristic function. And this will lead us to have, due to this e to the 2 pi I u omega term, to estimate the Fourier transform of the Dirichlet polynomial. That looks like this. Okay. So remember, if when you have a Fourier transform like this, so that's something like e to the I z, say you can use the series approximation of e to the I z, and you can write the Fourier transform, you can write an approximation for the Fourier transform as a sum over iz to the k over k factorial for k up to some limit that you can choose. So this sum here will be a sum of the moments actually. And once you do that, using some comparison in between the moments of the real part of the polynomial and the real part of the random polynomial, you can write this Fourier transform in terms of the Fourier transform in the random domain. And what you will have is that you will have this NT, again, from the diagonal term, similar to the calculation of the discrete moments. Then you will also have a minus t over 2 pi term that comes from Landau formula. And of course, everything here will be made precise. I just don't show everything here. And once you do that, once you plug in this Fourier transform to here, you can find an expression, you can find an estimate for the sum of f of y vectors. Okay. Atul, how am I doing with time? Am I 2:22? Okay. I'll try to finish, I guess, in 8 minutes. Is that true?
More time
Okay.
if you wish.
Okay. Okay, so now, again, by using this initial expression that we had for the characteristic function of the interval, we will be able to find a precise result for this distribution function of the real part of the polynomial. So these are some ideas that goes into this. Okay. Okay. So now about the some final remarks on some consequences of these results. So we have a corollary for the logarithm of the derivative. So the story starts with a result of Hedgehog. So this is a continuous result. So this has the Lebesgue measure here, and he showed that assuming a reach, so for the logarithm of the zeta prime divided by log t, so this time you have to divide with log t, you have a similar central limiter. And this was made more precise and also unconditional by Selberg a few years later. Okay, so this is a continuous result. What else Hedgehog did was prove sort of a discrete version of his result. So he assumed that all the zeros have to be simple so that he is able to consider the real part of the logarithm at zeta prime rho. And then he assumed that Riemann hypothesis holds and zero spacing hypothesis that was dependent on some parameter alpha hold. This hypothesis I showed in the beginning of the talk. So he showed that asymptotically this distribution function is the same as the distribution of the standard Gaussian. Okay. So can we say something about the error term, right? So this was our question that we handled. So remember, we have a central limit theorem for the real part of the logarithm of zeta that that hold for this sequence here. So what we do is that we assume that all of these multiplicities, they are just one. And then what we do is we assume that, so in the beginning we assume that v is 0 and then all the multiplicities are 1. And then what we are left with is this function here. So logarithm of the thing in this parentheses. So the only variable here is u. And once we let u to 0, the second term u log t over 4, that will vanish. And then we will have that this zeta rho plus u minus zeta rho over u, that will give us the zeta prime. And then we'll have an extra e log t over 4. But the thing is that e over 4 there, it doesn't really matter. It can just end up in the error term as a constant. So what we do is that e over 4 still ends up in the error term in the distribution. So we assume that all the zeros are simple. We assume the Riemann hypothesis and Montgomery's pair correlation conjecture. And we get an explicit error term for Hedgehog's result. So this is just a corollary, but independent of this corollary, using the same ideas, we can still show that instead of Montgomery's pair correlation conjecture, we can use the zero spacing hypothesis that Hedgehog used, and then we can still obtain an error term. So we can make our result stronger. Okay. And the final remark is that we can generalize these results. So usually when you have a result for the zeta function, you expect to have that result hold for the Dirichlet L-functions, and even actually for more general arithmetical functions. So to have a generalization, we now assume the generalized Riemann hypothesis. So all the zeros of this L function lie on the critical line. Since we will look at the L function at the non-trivial zeros of the zeta function, we need to assume that the L function do not vanish at the zeros of the zeta function. And we expect to have the same distribution results. If we assume some zero spacing hypothesis that holds between zeros of the L function that you have and the zeros of the zeta function, and then you would also have a result for the real part of the logarithm of the L function. So these are looking at the L function, the values of the L function at the sequence of the zeros of the zeta function. In general, of course, what you can do is you can look at the logarithm of an L function at the zeros of another L function. So these ideas, they most probably can be generalized. Okay, so that was the final thing. And I want to thank you for everyone for coming to my talk. And again, thank you for Goral and Atul for inviting me to speak. That's what it's, yeah.
Thank you, Fatma. Thanks for the nice talk. I had a couple of questions, if I may ask. So the first one was regarding your corollary that you had on towards the end of the talk. Is that error term, is that sharp?
Yeah, I mean, so the thing is, we expect this to be really close to the truth.
Okay.
I think we may expect, so not even for this, but even for, you know, the regular, I mean, the usual central limit theorem for the Riemann zeta function. So if everything was perfectly random, so you can think of the perfect situation for, you know, the random polynomial, for example. You can ask, what was the central limit theorem like for the random polynomial? Because that will be the perfect random situation. That will be far from what we have here. I think in that case, you would have something like 1 over square root log x, where x is the length of the random polynomial.
Mm-hmm.
So this is really close to the ultimate truth, I think. Yeah.
Okay, nice. And this you are able to very easily get from your general result, right? You take v equal to 0 and then you let u tend to 0, and then that gives nicely the zeta prime at rho.
Yeah,
so that's really nice to see.
Yeah, that was I guess like a surprise of this, but the thing that is a bit I don't know if it is surprising, but it's probably not surprising. But you can't do the same for the argument of zeta prime, because you don't have that term that allows you to, you know, have seen the derivative of the zeta prime of zeta. So that works for the real part, but it doesn't unfortunately work for the imaginary part.
Okay. And I had one other question that was, I'm really surprised to see the Beurling-Selberg function, where you approximate the signum function by means of this complicated looking integral. What was the origin of such function? I mean, how did they come up with this?
Yeah. So I think first Beurling came up with these in 1930s, I think. And then Selberg came up with these independently. And I think he didn't really know beforehand that Beurling actually was able to show that these functions exist. I think the way Selberg does it is from large, I think the way Selberg does it is finding some optimizing function in the large sieve. But I don't know how Beurling obtained these functions. So,
okay.
Yeah, this is in an article of Selberg in I think in collected works of L-functions, volume 2. I think when he talks about the large sieve, he mentions these functions.
Okay, thank you. We have some other questions. They are in this chat box. So I'll just read out those. So Professor Ajit Iqbal Singh, she has asked about elaborating on this small powers of t. I think this was somewhere in the middle of your lecture where...
I see. So having x a small power of t, I think, right?
Right, when you had
so what
x less than or equal to t squared.
Yes, you had log x, log x, and then you said when x is a small power of t. So I wondered what small power of t means.
Yeah. So in general, you want in this problem, you want something like t to 1 over log t, say, something like that. If you pick something like that, some x like that, it will work for the whole problem. For moment computations, you can get away with something larger, but for the distribution function, you need an x that is smaller. So in general, I would say t to the power 1 over log t, something that looks like that.
My worry was if power is allowed to be less than 1, and when it approaches 0, then you get some negative term going to minus infinity.
Right. So what you do is that won't happen. It's just that you need to have which usually what you do is you start with something like t to the 1 over 8k.
Okay.
Power. And then you pick x to be smaller than that, and then you sort of show that gap in between them do not matter.
Okay, so thank you for elaborating. Thank you.
Thank you.
Very nice, very nice. Good asymptotics.
Thank you.
Any other questions from the audience?
So I have a question. So you took z is u plus iv, where u lies between 0 to c over log t. So
right.
Can we take c as arbitrarily small?
Right. That c is a fixed, in that case it's a fixed
Okay.
So in this discussion, for this slide that I show, you need to assume that c doesn't really depend on t or anything. C is just a fixed constant.
Okay, so we have to fix. Okay, I have another question. So you pick up the points from the critical strip with the left of the right of the critical line.
Right.
So if you took the points from the left side of the critical line, is it a similar type of distribution happening?
Yeah. So in that case, you can remember the function equation that had,
yeah. Okay.
Yeah,
so from, it's direct from functional equation, right?
Yeah, I think you would just have you probably will have a different mean as well. So even in the usual Selberg central theorem, in there we assume that on the critical line. And here I stated this to the left of the critical line. So I didn't say anything about what is to the right of the critical line. What you can do is you can get, you can still get slightly to the right of the 1/2 by say something like 1/2 minus log t. I think in that case, mean will be non-zero. That means probably find from the functional equation.
Okay. I mean, so you are not confirmed at the time, right?
Yeah, we just don't really deal with that part because really from the functional equation you can work on one side of the line most of the time. So we just focus on that.
Okay. So yeah, one more question. So in the conclusion remark, so the error term you're talking about, so is it depend upon the conductor, or how can we take any conductors?
Since it is still current work, I can't really say much about the conductor for now. Yeah, I would rather say nothing about that for now.
Okay. Yeah, so actually I found the Selberg result on the linear combination. He actually restrict the conductor, like conductor is square root of t. So
yeah,
therefore,
power of t. Yeah, that will make sense, right?
Yeah. Okay, thank you very much.
Thanks.
Any other question? Okay, if not, let's thank Fatma again for a very nice talk, and we'll resume in 2 weeks from now. So next Thursday. Thanks, everyone.
Hey, everyone.
See you all. Bye.